Right now, as you read these words, the galaxy is on fire. Not in the way a building burns, not in the way a forest collapses into smoke and ember. It burns slowly, magnificently across distances so vast that the light from those flames will travel for tens of thousands of years before it reaches the edge of its own home. 400 billion stars. Each one a furnace of hydrogen and helium fusing under pressures no laboratory on Earth has ever replicated, each one broadcasting energy in every direction simultaneously. Each one warming the dark in its own small corner of an incomprehensibly large spiral of gas and dust and ancient light. 400 billion. If you tried to count them one per second without sleeping, without stopping, without pausing for a single breath, you would need more than 12,000 years to finish. You would have started before the invention of the wheel, before the first city was built, before agriculture existed, before writing, before any civilization now remembered had drawn its first breath, and you would still not be done today. This is the Milky Way. This is our home. And by every measure science has developed to assess the probability of life, it should be teeming. Not possibly teeming, not speculatively teeming. Mathematically, statistically, almost certainly teeming. NASA's Kepler Space Telescope, which spent 9 years staring at a small patch of sky containing roughly 1,500,000 stars, determined that planets are not the exception in this galaxy. They are the rule. Nearly every star has them. And approximately 1 in 5 sun-like stars hosts at least one rocky, Earth-sized world, sitting at the precise distance from its parent star, where liquid water can exist on the surface. Liquid water. The one substance that every form of life we have ever discovered on this planet requires above all else. Apply that ratio to the Milky Way's population of sun-like stars alone, and the number of potentially habitable worlds exceeds 11 billion. 11 billion. And that figure does not include the planets orbiting red dwarf stars, which are far more numerous than stars like our Sun. Include those, and the number of worlds where life might plausibly arise climbs to tens of billions. Tens of billions of candidates, in a galaxy that has been producing stars and planets for over 13 billion years. The chemical ingredients for life are not confined to Earth either. Astronomers have detected complex organic molecules drifting in the cold gas clouds between stars. Amino acids, the molecular building blocks from which proteins are assembled, have been found inside meteorites that fell to Earth's surface from the outer solar system. Water ice exists on the moons of Jupiter and Saturn beneath the crusts of worlds that never see direct sunlight. The raw materials of biology are scattered across the galaxy, the way dust is scattered across a sunlit room everywhere, in quantities that beggar any attempt at precise measurement. This is the foundation. This is the mathematical bedrock upon which every serious scientist who has ever thought carefully about the question of extraterrestrial intelligence has stood. The galaxy is old, habitable worlds are abundant, the chemistry of life is commonplace, the time available for evolution to work, its patient, grinding, merciless process is measured not in millions of years but in billions. Every factor we can quantify points toward the same conclusion. We should not be alone. We should not even be close to alone. And yet, listen, nothing, absolute silence. In the 65 years since humanity first deliberately aimed a radio telescope at another star and listened for signals, we have detected nothing that can be confirmed as the product of an intelligence other than our own. No radio signals, no laser pulses, no repeating patterns embedded in the noise of the cosmos that suggest someone somewhere is trying to be heard. We have surveyed millions of stars across dozens of frequencies. We have scanned 100,000 galaxies for the infrared signature of civilizations harvesting the energy of their own suns. We have examined our own solar system for artifacts, for probes, for any physical evidence that a visitor ever passed through our neighborhood in the 4.5 billion years our planet has existed. Nothing, not a whisper, not a ghost of a signal, not a single anomaly that has survived rigorous scrutiny and been confirmed as artificial in origin. The universe had 13.8 billion years to produce something that could wave at us. And either it did not, or whatever it produced does not wave. Both possibilities are in their own distinct ways, among the most disturbing ideas the human mind has ever been forced to contemplate. If you are the kind of person who finds that the biggest questions science can ask are also the ones most worth sitting with, do me a small favor and hit that like button and subscribe to this channel. It genuinely helps this work continue, and it lets me keep making these journeys with you. Every subscriber is a signal in the dark, and in the context of what we are about to explore together, that metaphor carries more weight than it might seem. Get comfortable, turn down the lights if you like. What follows is not a simple story with a reassuring ending. It is one of the deepest, most unresolved, and most consequential puzzles in the history of human thought. And the reason it matters is not academic. The reason it matters is that the answer, whatever it turns out to be, says something profound about us, about what we are, about how long we are likely to last, about whether the lights we are keeping on here on this small world, in this quiet corner of the galaxy, will still be burning 1,000 years from now. Let's begin. It was an ordinary Tuesday in the summer of 1950. The desert heat pressed down on the mesa at Los Alamos, New Mexico, where the United States government had built a secret city during the war, and where 5 years after the war ended, some of the most brilliant physicists alive still gathered to think and work and argue. The laboratory had changed its mission after Hiroshima and Nagasaki. The weapons were built. The era they had inaugurated was already reshaping every political calculation on the planet. But the minds that had assembled there remained, and on this particular Tuesday, several of them were walking together toward the cafeteria for lunch. The conversation was light. Someone had mentioned a recent cartoon in the New Yorker depicting aliens stealing trash cans from the streets of New York City. It was a gentle joke about the flying saucer reports that had been filling the newspapers that year, the summer of strange lights and unexplained aerial phenomena that had captured public imagination and generated more column inches than any serious scientist thought the subject deserved. The physicists laughed. The topic drifted. By the time they reached the cafeteria, they had moved on to other things. Then, in the middle of lunch, with no particular preamble, with no dramatic pause or portentous shift in tone, Enrico Fermi set down his fork. "Where is everybody?" His colleagues laughed. The question sounded like the punchline of a joke that hadn't been told yet. But Fermi was not joking, and the people at that table knew it because they knew Fermi. They knew that behind the casual delivery was one of the most formidable calculating minds of the 20th century. This was the man who had built the world's first nuclear reactor beneath the stands of a squash court at the University of Chicago. This was the man who, during the first test of the atomic bomb in the New Mexico desert in 1945, had estimated its yield by dropping scraps of paper into the blast wave and measuring how far they traveled. His intuitions were not idle. When Fermi asked a question that sounded simple, the simplicity was a surface. He had been running numbers in his head on the walk to the cafeteria. Numbers about stars and time, and the probability of planets, and what ought to follow from that probability if intelligence was not vanishingly rare. The calculation was rough, informal, the kind of order of magnitude reasoning he was legendary for, but the conclusion it pointed toward was stark. Given the age of the galaxy, given the number of stars it contained, given how long the process of biological and technological evolution would need, even under conservative assumptions, to produce a civilization capable of reaching other star systems. Given all of that, the Milky Way should have been colonized many times over. Signals should be detectable across every frequency. Evidence of intelligence should be visible from the surface of any world equipped with the right instruments. And yet humanity, looking outward with the best instruments it possessed, found nothing. Edward Teller, who was sitting at that table, later recalled that Fermi had made a series of rapid calculations and arrived at the conclusion that there was a profound contradiction between what the mathematics predicted and what the evidence showed. The probability said they should be here. Reality said they were not. Something in the assumptions that led from one to the other had to be deeply fundamentally wrong. Fermi never published a paper on this. He never formalized the argument, never presented it at a conference, never returned to it in any systematic way before his death, 4 years later in 1954. It was a lunchtime observation, A question asked between bites of food in a cafeteria in the desert, and yet it has never been answered. 75 years later, with instruments that would have seemed miraculous to Fermi, with computers that can process more data in an afternoon than the entire scientific community of 1,950 could have processed in a decade, with a map of the galaxy that now includes the positions and properties of nearly 2 billion stars. The question he asked between bites of food in a New Mexico cafeteria remains open. Where is everybody? This is the Fermi Paradox, and it is not, despite how it sometimes gets described, merely a philosophical puzzle. It is not a thought experiment to be resolved by clever argument or dismissed as unanswerable and therefore unimportant. It is an empirical observation, a data point. The silence is real, measurable, and increasingly difficult to explain away as the decades of searching accumulate without result. To understand why the silence is so disturbing, you need to understand the specific shape of the expectation it contradicts. You need to see the numbers the way Fermi saw them at that cafeteria table, and then you need to see how those numbers have been refined, expanded, and made more precise in the decades since. Because the more precisely we measure the factors that should determine how many civilizations exist in this galaxy, the harder the silence becomes to explain. Start with time, not human time, not historical time. Geological time is not even adequate here. We are talking about galactic time, the kind of time that makes 4.5 billion years, the entire age of our solar system, look like an afternoon. The Milky Way began forming approximately 13.6 billion years ago. Our sun ignited around 4.6 billion years ago, which means the galaxy existed for 9 billion years before our star was born. 9 billion years. During that span, other stars formed, lived their lives, and died. Heavier stars burned fast and exploded as supernovae, seeding the interstellar medium with carbon, oxygen, iron, and every other element heavier than hydrogen and helium. Successive generations of stars formed from this enriched material, and around them rocky planets assembled from the debris. The oldest stars in our galaxy that sit in the right conditions for rocky planet formation have been burning for more than 10 billion years. A civilization that arose around one of those older stars, even a civilization that evolved at precisely the same sluggish pace as life on Earth, would have had a head start of 5 billion years over us. 5 billion years ago, Earth did not exist. The atoms that now make up your body were dispersed across an interstellar gas cloud. If intelligence follows from biology with any reasonable frequency, then civilizations that emerged around older stars should have reached technological maturity billions of years before the first microbe appeared in Earth's oceans. And here is where the mathematics becomes genuinely disquieting. You do not need faster than light travel to cross a galaxy given enough time. You do not need warp drives or wormholes or any technology beyond a modest extrapolation of what humanity has already begun to develop. In 1980, the physicist Frank Tipler demonstrated with careful calculation that a civilization possessing only the technology to build self-replicating robotic spacecraft, machines capable of traveling between stars, and using local resources to construct copies of themselves upon arrival, could saturate the entire Milky Way within 1 to 10 million years. 1 to 10 million years. The galaxy is 13 billion years old. 1 million years represents less than 1/100th of 1% of that history. If even a single civilization anywhere in this galaxy at any point in the past 13 billion years had developed self-replicating probes and launched them, those probes would have reached our solar system billions of years ago. They would be here now. They would have been here since before the dinosaurs walked the Earth. We see no such probes. We find no artifacts in our solar system that cannot be explained by natural processes. The moon's surface, which preserves a record of every significant impact event for the past 4 billion years, a fossil record written in craters, shows no sign that anything artificial ever passed through our neighborhood. The Lagrange points the gravitationally stable regions of our solar system, where a probe might park itself indefinitely, have been searched. Nothing. The expected result of 13 billion years of cosmic history, given any reasonable assumption about the emergence of intelligence, was a galaxy crowded with evidence of minds. The observed result is a galaxy that looks in every direction we can examine, as though nothing capable of building a radio telescope has ever existed anywhere within it. Except here, except us, except right now. That is the Fermi Paradox. Not as a philosophical curiosity, as a fact about the universe that demands an explanation. And the explanations that are available when examined carefully are either deeply strange or deeply unsettling, or in many cases both. We are going to examine all of them. In 1961, 11 years after Fermi asked his question over lunch, a young astronomer named Frank Drake stood in front of a blackboard at the Green Bank Observatory in West Virginia and wrote an equation. He was not trying to solve the Fermi Paradox. The paradox as a formal scientific problem had not yet fully crystallized in the scientific community's mind. Drake was doing something more modest. He was organizing a conversation. The occasion was the first serious scientific conference ever convened on the question of extraterrestrial intelligence. A small gathering of researchers, 11 in total, had assembled at Green Bank to discuss whether it was scientifically reasonable to search for signals from other civilizations and, if so, how such a search might be conducted. Drake needed a framework. He needed a way to break an enormous, unwieldy question into smaller pieces that could be discussed, estimated, and argued about one at a time. So, he wrote the equation on the blackboard before the meeting began, not as a calculation but as an agenda. The Drake equation, as it became known, multiplies 7 variables together to estimate the number of communicative civilizations currently present in the Milky Way. Each variable represents one link in a long chain of causation that runs from the raw material of stellar formation all the way to a civilization sitting at a radio transmitter, sending signals into the dark. The equation is elegant. It is also, when you look at it honestly, a precise map of human ignorance, because most of its variables, when examined carefully, dissolve into uncertainty so profound that the equation can produce answers ranging from less than 1 to several million, depending entirely on the assumptions you feed it. Understanding the equation means understanding exactly where the Fermi paradox bites and exactly where our knowledge ends and speculation begins. The first variable is the rate at which new stars form in the Milky Way. This is the most solid number in the entire equation. Astronomers have measured it through multiple independent methods, counting young stellar objects, measuring infrared emission from star-forming regions, tracking the rate of supernova explosions that mark the deaths of massive, short-lived stars. The consensus figure is approximately 1.5 to 3 new stars per year. Call it 2. This number is well constrained. It does not vary dramatically between different measurement approaches. It is the one place in the Drake equation where you can plant your feet on solid ground. The second variable is the fraction of those stars that form planetary systems. Here, for the first time, the ground begins to shift. When Drake wrote his equation in 1961, this fraction was essentially unknown. A handful of theoretical arguments suggested planets might be common, but direct observational evidence was almost entirely absent. The first confirmed detection of planets orbiting another sun-like star would not come until 1995, 34 years later. What the intervening decades of observation revealed was extraordinary. Planets are not merely common, they are essentially universal. The Kepler mission, the Transiting Exoplanet Survey satellite, and ground-based radial velocity surveys have collectively demonstrated that the vast majority of stars host planetary systems of some kind. Current estimates place the fraction at close to 1, not close to 1/2, not close to 3/4, close to 1, meaning that when a star forms, the formation of planets around it is not a lucky accident. It is the default outcome of the same physical process that creates the star itself. The protoplanetary disk of gas and dust that surrounds a young star almost inevitably produces worlds. The fraction Drake had to guess at in 1961 turns out to be nearly as well constrained as the star formation rate. Almost every star has planets. The third variable is the average number of planets per star system that could potentially support life. This is where the equation begins to open up into genuine uncertainty. Not every planet in a given system sits in the right location. Not every world has the right composition. The habitable zone, the range of orbital distances where a planet receives enough stellar energy to maintain liquid water on its surface under Earth-like atmospheric conditions, is a specific band, and only some planets fall within it. But the Kepler data suggests that rocky Earth-sized planets in habitable zones are not rare. They appear around roughly 1 in 5 Sun-like stars, and potentially more frequently around the smaller, dimmer red dwarf stars that make up the majority of the galaxy's stellar population. Furthermore, the definition of habitability has expanded considerably since Drake first wrote his equation. Europa, one of Jupiter's moons, has a global liquid water ocean beneath its icy crust, maintained not by sunlight, but by tidal heating from Jupiter's gravity. Enceladus, a moon of Saturn, vents water vapor and organic molecules from a subsurface ocean through cracks in its surface. These worlds exist well outside the traditional habitable zone, yet they carry liquid water. If life can arise in such environments, the number of potentially habitable worlds in our solar system alone expands from 1 to at least 3, possibly more. Scale that to the galaxy, and the numbers become extraordinary. Conservative estimates place the average number of potentially habitable worlds per star system at somewhere between 1 and 5 among systems that have any habitable zone candidates at all. This remains an uncertain figure, but it is uncertain on the high side. The universe appears to be generous with the conditions that life, at least life as we understand it, requires. The fourth variable is the fraction of habitable worlds on which life actually appears. And here for the first time, the equation encounters a wall. We have exactly one data point. This is the fundamental epistemological crisis at the heart of astrobiology. Life exists on Earth. We do not know whether it exists anywhere else. We do not know whether its appearance on Earth was a routine consequence of chemistry, given the right conditions, or whether it was a fantastically improbable accident that could have easily not happened at all. We have one example of a living world, and we do not know how representative that example is of the broader cosmic population. What we can say is this: life appeared on Earth relatively quickly. The planet formed approximately 4.5 billion years ago. For the first several hundred million years, its surface was a hellscape of volcanic activity, meteorite, bombardment, and surface temperatures incompatible with biology. By approximately 3.8 to 4 billion years ago, within a few 100 million years of conditions stabilizing microbial life was already present. The geological record shows microbial signatures in rocks that age. Life did not wait long. Given a habitable world life appeared at something close to the earliest moment the physical record is capable of preserving. Some scientists read this as evidence that abiogenesis, the transition from complex chemistry to self-replicating biology, is easy. If the process were so improbable that it might fail to occur on any given habitable world, you would expect it to take much longer when it did occur, the way a very difficult lock takes time to pick, even by an expert. The relative speed of life's appearance on Earth, this argument goes, suggests that the lock is not especially difficult. Given liquid water energy and the right chemical environment, life bootstraps itself into existence with reasonable reliability. But the counter-argument is sobering, and it rests on a simple logical point. We are here to observe that life arose quickly on Earth precisely because we are alive. If life had not appeared on Earth, no one would be here to note the absence. This is the anthropic selection effect, and it means we cannot use the speed of life's appearance on our own planet as unbiased evidence about how easy abiogenesis is in general. The only planets from which observers can report are planets where observers exist. We are guaranteed by the logic of our own existence to find ourselves on a world where life arose. The question of how many other worlds share that property cannot be answered by examining ours alone. This is not a trivial point. It is not a philosophical technicality. It means that the fourth variable in the Drake equation, arguably the most important variable after the final one, is genuinely unknown and may remain unknown until we either find life somewhere else or definitively confirm its absence across a large enough sample of worlds. Neither achievement is close. The fifth variable is the fraction of life-bearing worlds where that life eventually develops intelligence, meaning the kind of cognitive sophistication that allows a species to manipulate its environment through technology to develop language complex enough to accumulate and transmit knowledge across generations and ultimately to build instruments capable of communicating across interstellar distances. Once again, one data point. But this time the single data point we possess is instructive in a way that is not encouraging for those hoping the galaxy is full of minds. Life existed on Earth for approximately 3.5 billion years before anything resembling human-level intelligence appeared. 3.5 billion years is not a rounding error. It is the bulk of Earth's biological history. During that span, evolution explored an extraordinary diversity of forms. It produced photosynthesis, multicellularity, sexual reproduction, eyes, limbs, nervous systems, and the Cambrian explosion of animal body plans. It produced 500 million years of vertebrate evolution. It produced dinosaurs that ruled the land for 160 million years. It produced insects that have been thriving in unbroken lineages for 400 million years. Out of all of that diversity across all of that time, spanning hundreds of millions of distinct species, exactly one developed technology. One. This is the number that should give anyone pause. Evolution is not trending toward intelligence. Evolution does not trend toward anything. It is a blind process that rewards reproductive success, and reproductive success can be achieved through strategies that have nothing to do with cognition. Bacterial lineages have been thriving for billions of years without a single neuron between them. Sharks have been essentially unchanged for 450 million years. They predate trees. They survived every mass extinction event that has occurred in the history of complex animal life. Their strategy involves hydrodynamic efficiency and sensory acuity, not reasoning. It has worked for almost 500 million years without generating the slightest movement toward technology. The specific evolutionary pathway that led to human cognition was contingent on a chain of events that easily might not have occurred. The asteroid impact 66 million years ago that ended the reign of the non-avian dinosaurs was not scheduled. It was not inevitable. It was a rock from space intersecting Earth's orbit at a particular moment. Without it, the small nocturnal insect-eating mammals that survived in the dinosaurs' shadow might still be small and nocturnal. The specific climatic and geological changes in East Africa that drove our ancestors toward bipedalism, tool use, and the social complexity that eventually produced language were products of particular tectonic and atmospheric conditions. Different conditions would have produced different pressures. Different pressures would have produced different adaptations. The paleontologist Stephen Jay Gould spent much of his career arguing that if you rewound the tape of evolution and played it again from the Cambrian explosion, the results would bear no resemblance to what we observe today. Intelligence might never reappear. The specific constellation of accidents and contingencies that produced a primate with 100 billion neurons capable of asking Fermi's question is not on the available evidence a predictable outcome of biological evolution. It looks much more like a peculiar accident, a lucky throw of a very complicated set of dice. The sixth variable is the fraction of intelligent species that develop technology capable of producing detectable signals. Radio transmissions, laser pulses, deliberate modifications to their star's energy output. Even on Earth, this step was not automatic. Anatomically, modern humans have existed for approximately 300,000 years. For the overwhelming majority of that time, we were invisible to the cosmos. We lived in small social groups, made tools from stone and bone, and left no trace detectable from beyond our atmosphere. The transition from biological intelligence to technological civilization occupied only the last fraction of 1% of our species' existence, and even then the specific technologies that made us detectable radio transmitters were invented only in the last century and a quarter. The window between the emergence of intelligence and the development of interstellar range signals is not guaranteed to open at all, and on Earth, it opened very recently, very narrowly, and in circumstances whose long-term stability is, as we shall examine in detail, far from assured. The seventh variable is the one that swallows all the others. It is denoted in the equation simply as L. It represents the average length of time that a communicative civilization survives, the average duration of the broadcasting window. How long from the moment a civilization first becomes detectable to the moment it goes silent do the signals last? This variable determines everything. A civilization that broadcasts for 10 million years fills a sphere of space, 10 million light-years in radius, with its signals. In a galaxy 100,000 light-years across, such a civilization becomes visible to virtually every inhabited world within it. A civilization that broadcasts for 200 years is a momentary flicker, so brief that the probability of any other civilization existing simultaneously and possessing the sensitivity to detect it becomes vanishingly small. When Drake and his 11 colleagues at Greenbank plugged optimistic values into every variable and arrived at estimates ranging from 1,000 to 100 million communicative civilizations in the Milky Way, the mood was hopeful. The universe seemed crowded. Contact seemed not merely possible, but perhaps imminent. The history of SETI as a scientific enterprise begins in that atmosphere of optimism, but the optimism was built on an assumption about L. It assumed that civilizations, once they arose and began broadcasting, tended to persist. That intelligence, once it appeared, was durable. That the same cognitive capacity that built a radio telescope would also, in the fullness of time, navigate the challenges that came with it and survive. That assumption has never been demonstrated, and the silence of the cosmos, after 65 years of listening with instruments far more sensitive than anything Drake possessed, suggests it may be wrong. The Drake equation does not answer the Fermi Paradox, but it does something equally valuable. It shows you precisely where the uncertainty lives. It tells you which questions you cannot currently answer, and it forces you to confront the most important one directly. Not how many stars form, not how common planets are, not even how probable life or intelligence might be. The most important question the equation asks is this: what happens to civilizations after they arise? Do they endure? Do they expand? Do they fill the sky with signals for millions of years, leaving traces that any telescope worthy of the name would detect? Or do they flame briefly in the dark and go out, leaving nothing behind but silence? The answer to that question is not written in the stars. It is written in history, in the decisions that civilizations make when the power they have acquired begins to exceed the wisdom with which they were equipped to manage it. And the historical record of the one civilization we can examine in detail is not on careful inspection a story of inevitable survival. But before we go there, before we descend into the territory, the Fermi Paradox opens up. When you follow it far enough, we need to understand the full weight of the silence itself. Not the theoretical silence predicted by equations, but the actual measured, documented silence accumulated by decades of listening. Because the silence is not just an absence, it is a quantity. It has been measured repeatedly with increasing precision across expanding regions of sky and spectrum, and the more precisely it has been measured, the more absolute it has become. That silence and the history of the search that documented it is where we go next. On the morning of the 8th of April 1960, a 30-year-old astronomer named Frank Drake climbed into the receiver room of an 85-foot radio telescope at the Greenbank Observatory in West Virginia and pointed it at a star. The star was Tau Ceti, a sun-like star approximately 12 light-years from Earth, close by cosmic standards, near enough that a radio signal traveling at the speed of light would need only 12 years to make the crossing. Drake had chosen it, and a second target, Epsilon Eridani, because they were among the nearest stars similar enough to our own sun that they might plausibly host planets capable of supporting life. He had chosen a frequency of 1420 MHz, the emission frequency of neutral hydrogen, because hydrogen is the most abundant element in the universe, and because any civilization with sufficient knowledge of physics to build a radio transmitter would know that frequency, would know that any other civilization searching for signals would likely to monitor it. It was in the language of game theory a focal point, a place where two parties who have never communicated might independently choose to meet. Drake called his project Ozma, after the queen of the fictional land of Oz, a ruler of a distant, exotic, and difficult-to-reach place. The name was whimsical, the science was not. For approximately 4 months, Drake and his small team listened. They processed the data. They watched for anything that deviated from the natural noise of the cosmos. A narrowband signal, a repeating pattern, any deviation from what physics alone would produce. They heard nothing. Project Ozma was not a failure. It was the opening move of a search that would consume decades, involve dozens of institutions across multiple countries, develop instruments of extraordinary sensitivity, and eventually survey millions of stars across a range of frequencies that Drake's 1,960 equipment could not have imagined. It was the first step on a very long road, but the road's destination 65 years later has not changed. The silence that greeted Drake's telescope in 1960 has greeted every telescope since. To appreciate the weight of that silence, you need to understand how much the search has grown. In 1960, Drake had one telescope, 2 target stars, 1 frequency, and 4 months of observation time. By the 1970s, SETI programs had multiplied. The Ohio State University Big Ear Telescope, a fixed radio telescope that could not be steered, but instead swept the sky as Earth rotated, ran a continuous sky survey throughout the decade. It was Big Ear that produced the one moment in the history of SETI that came closest to changing everything. August 1976. A volunteer astronomer named Jerry Eman was reviewing a printout of data recorded by Big Ear 6 days earlier, sitting at his kitchen table, going through columns of numbers and letters that represented signal intensity at various frequencies. The data was printed in a format where each character represented a specific signal strength on a scale from 1 to 9, and then continuing through the letters of the alphabet. Background noise typically produced 1s and 2s, occasionally a 3. The natural radio environment of the cosmos is mostly quiet at the frequencies SETI programs monitor, punctuated by known natural sources that the researchers had catalogued and learned to recognize. What Eamon found in that printout was not quiet. A sequence of characters read 6EQUJ5. On the intensity scale, the telescope used the peak character U, represented a signal strength of 30 times the background noise level. The signal lasted exactly 72 seconds, which was precisely the duration expected for a genuine point source in space, passing through Big Ear's fixed beam as Earth rotated. It came from the direction of the constellation Sagittarius. It appeared at a frequency close to the hydrogen line that Drake had identified 15 years earlier as the logical meeting place for civilizations attempting to make contact. It was narrowband, meaning it occupied a very small slice of the radio spectrum, which is a characteristic of artificial transmissions. Natural astrophysical sources tend to emit across broad ranges of frequency. The narrow focus of this signal was consistent with what an intentional broadcast would look like. Eamon circled the sequence on the printout and wrote a single word in the margin. Wow. For a brief, extraordinary moment, it looked like contact, but the signal was never heard again. Eamon and other researchers pointed telescopes at that same patch of sky hundreds of times over the following months and years and decades. Other instruments joined the search. More sensitive equipment was brought to bear. The coordinates were watched, waited on, and listened to, with a patience born of the understanding that what might have been detected there was the most important thing any human being had ever found. And every time, the result was the same. Silence. Without repetition, a signal cannot be confirmed. Without confirmation, it cannot be attributed to an artificial source with scientific confidence. Natural phenomena can produce unusual radio bursts. Terrestrial interference, despite Big Ear's precautions, could not be ruled out with certainty after the fact. The WOW signal remains more than 45 years after Eamon circled it at his kitchen table, the most tantalizing detection in the history of SETI. It also remains unconfirmed. A single burst that might have been everything or might have been nothing, with no way to determine which. The most frustrating kind of evidence there is evidence that raises a question it cannot answer. The WOW signal was the high water mark. Everything since has been lower. Through the 1980s and into the 1990s, SETI programs continued to expand. NASA entered the search in 1992 with the High-Resolution Microwave Survey, an ambitious systematic scan designed to examine millions of frequencies across the entire sky, with sensitivity far exceeding any previous effort. The program was cancelled by the United States Congress after a single year defunded in a budget vote, accompanied by ridicule from legislators who characterized it as a search for little green men. The mockery was not scientifically informed, but it was politically effective. The funding disappeared. Private donors stepped in to continue the work. The SETI Institute, a non-profit research organization, carried the search forward with Project Phoenix, which surveyed approximately 800 nearby star systems over the course of a decade using some of the world's largest radio telescopes. The Arecibo Observatory in Puerto Rico, for decades, the most sensitive radio telescope on Earth, contributed observation time. The Parkes Observatory in Australia extended the search into the southern sky. Project Phoenix was meticulous, patient, and thorough. It heard nothing it could confirm as artificial. The scale of the modern search expanded dramatically in 2015 when the Russian-born entrepreneur Yuri Milner announced a commitment of $100 million to a new SETI initiative called Breakthrough Listen. The program was designed to be the most comprehensive search for extraterrestrial intelligence ever conducted. It would survey the 1 million stars nearest to Earth. It would examine the entire plane of the Milky Way. It would look at the 100 nearest galaxies beyond our own. It would cover a frequency range from 1 to 12 gigahertz and process data at a rate that dwarfed the combined output of every previous SETI program in history. Breakthrough Listen secured observation time at the Green Bank Telescope in West Virginia, the same observatory where Drake had run his first search 55 years earlier, now vastly more sensitive than anything Drake had access to. It also used the Parkes Observatory in Australia and subsequently expanded to additional facilities. The computing infrastructure required to analyze the data it generated was itself a remarkable technical achievement. As of the mid-2020s, Breakthrough Listen has surveyed millions of stellar systems. It has processed quantities of data that would have been unimaginable to the pioneers of SETI. It has detected thousands of unusual signals, each one requiring investigation. Each one ultimately explained by terrestrial interference, no natural astrophysical sources or instrumental artifacts. Not one has survived scrutiny as a candidate for artificial extraterrestrial origin. The search has not been limited to radio. The development of optical SETI programs extended the search into a different region of the electromagnetic spectrum, looking for brief, intense laser pulses that an advanced civilization might use for communication or for propelling spacecraft. A laser pulse lasting a nanosecond but carrying enough energy to be detectable across interstellar distances would appear to a properly equipped telescope as a flash brighter than any star. Multiple optical SETI programs have scanned tens of thousands of stars for such pulses. None has been found. The search has also extended beyond signals entirely reaching toward physical evidence of civilizations at the largest possible scales. In 2015, a team of astronomers using data from the Wide Field Infrared Survey Explorer spacecraft surveyed approximately 100,000 galaxies, looking for excess infrared radiation consistent with the waste heat that a galaxy-spanning civilization would produce if it had harnessed a significant fraction of its host galaxy's stellar energy output. The concept originated with the physicist Freeman Dyson and the Soviet astronomer Nikolai Kardashev, who proposed in the 1960s that the most advanced possible civilizations would be detectable not through their communications but through their energy consumption. A civilization that had colonized an entire galaxy and built structures to capture stellar energy on a galactic scale would radiate that energy as heat, and that heat would show up in infrared surveys as an anomaly, a galaxy that was warmer than its stellar population alone could account for. The survey found nothing anomalous. 100,000 galaxies examined for evidence of the most advanced possible civilizations, and not one showed a signature that required intelligence to explain. A separate infrared survey examined 250,000 individual stars within the Milky Way, searching for partial Dyson structures, hypothetical megastructures built around individual stars to capture their energy. The survey found one star designated Keek 84622852 and nicknamed Tabby's star after the astronomer Tabetha Boyajian, who first analyzed its unusual behavior that showed a pattern of brightness fluctuations unlike any known natural phenomenon. For a period of months in 2015 and 2016, Tabby's star was the subject of intense scientific scrutiny and considerable public excitement. Subsequent observation and analysis ultimately attributed its unusual dimming to clouds of dust, a natural explanation, albeit an unusual one. The excitement faded. The star joined the list of candidates investigated and found to have mundane explanations. In 2020, a team of Australian astronomers published the results of what was at that time the most comprehensive SETI survey of its kind. Using the Murchison Wide Field Array in Western Australia, a telescope designed to observe the low-frequency radio sky, they examined over 10 million stellar sources in the southern sky, searching for narrowband signals consistent with artificial transmission. The scale of the survey was on. Each of these searches, from Drake's 4 months in 1960 to the decade-long continuous operations of Breakthrough Listen, has returned the same answer. And the answer is not nothing in the sense of an absence of data. The answer is nothing in the sense of a very large, very precise measurement of silence. These programs have recorded quantities of data measured in petabytes. They have identified and categorized thousands of signals, each one rigorously examined and each one explained. The silence is not the silence of inattention. It is the silence of listening carefully for a very long time and hearing only the natural hum of a cosmos that appears in every direction accessible to our instruments, devoid of any mind other than our own. This is the point at which the casual dismissal of the Fermi Paradox becomes impossible to sustain. The response that sometimes arises in popular discussion that we have barely looked, that the galaxy is vast, and our search has only scratched the surface, contains a kernel of truth but misses the deeper point. It is true that we have not surveyed every star at every frequency with maximum possible sensitivity. It is true that the search is incomplete, but the argument from incompleteness ignores what the search has actually found, which is that in every region of sky, we have examined with sufficient sensitivity across every frequency range our instruments can cover. The answer is the same. Furthermore, the argument from incompleteness does not address the physical expansion problem at all. The silence of radio telescopes might be explained by the limitations of radio astronomy. The silence of infrared surveys of 100,000 galaxies is harder to explain. A civilization that had colonized even a modest fraction of its host galaxy would produce an infrared signature detectable at extragalactic distances. We have looked at 100,000 galaxies. We found no such signature in any of them. The Gaia spacecraft, launched by the European Space Agency in 2013 to create the most precise three-dimensional map of the Milky Way ever constructed, has measured the positions, distances, and motions of nearly 2 billion stars. If civilizations had constructed large artificial structures or significantly modified their stellar environments in ways that affected a star's gravitational influence or proper motion, those modifications might appear as anomalies in Gaia's data. The data has been extensively analyzed. No such anomalies have been identified. The Moon deserves particular mention in this context. The lunar surface has been accumulating a record of everything that has passed through our solar system for the past 4 billion years. Meteorite impacts have garnered the regolith mixing and churning the surface material, but the record of large impacts of significant objects that approached our inner solar system is preserved in the crater distribution. If self-replicating probes had visited our solar system at any point in the past several billion years, the probability that they left no physical trace whatsoever, no artifact on the lunar surface, no material in stable orbital and configurations, no detectable modification to anybody in our solar system is extraordinarily small. We have examined the Moon extensively. We have placed seismometers on its surface, mapped its gravity field, analyzed samples returned by Apollo missions and lunar meteorites. We have sent spacecraft to orbit it, photograph it at high resolution and probe its interior. The Moon is, by the standards of any object in the solar system, extremely well characterized. It shows no sign of artificial modification. Nothing on its surface requires intelligence to explain. The silence, in other words, is not merely acoustic, it is physical. It is present in the infrared spectrum of distant galaxies. It is written on the face of our own moon. It is embedded in the orbital dynamics of every body in our solar system that we have measured precisely enough to detect deviations from natural gravitational predictions. The silence is everywhere we look, and it deepens with each passing year, each new telescope, each expanded survey. Not because we are finding evidence against intelligence, but because we are finding nothing at all, and nothing in this context is a very loud signal. It tells us that whatever is going on out there, it is not what the naive application of the Drake equation predicts. Something is wrong with our assumptions. Either the galaxy contains far fewer civilizations than the mathematics suggests, or those civilizations behave in ways that make them undetectable, or something about the nature of intelligence itself, about what happens to civilizations after they arise, is profoundly different from what the optimists at Green Bank assumed in 1961. The silence does not tell us which of these possibilities is correct. That is what makes it a paradox rather than a solved problem. But it does tell us something with considerable force. It tells us that the universe is not in any direction we can examine the bustling, signal-filled place the early SETI pioneers hoped and expected to find. And it asks with a persistence that 65 years of searching has only intensified why. The possible answers to that question are where the real darkness begins, because some of them are merely strange, and some of them are terrifying, and a few of them say something very specific about us, about this moment, about the century we are living through right now. We are about to examine all of them. The human mind does not tolerate uncomfortable silences well. It is not built for them. The same cognitive architecture that allowed our ancestors to detect predators in rustling grass, to find patterns in the behavior of prey animals, to read intention in the faces of other humans, compels us toward explanation. Silence in the evolutionary context in which our brains developed was never just silence. It always meant something. And so when confronted with the vast measure, carefully documented silence of the cosmos, the mind reaches immediately for reasons, for stories that make the emptiness sensible, for frameworks that transform the absence of evidence into something other than evidence of absence. Some of those frameworks are scientifically serious, some are philosophically interesting, some are both. And each one, when examined with sufficient care, reveals a hidden assumption so large and so difficult to justify that the explanation collapses under its own weight. The easy answers are not easy because they are obviously wrong. They are easy because they feel satisfying. They resolve the tension without requiring us to confront the darker possibilities. And that comfort, that feeling of resolution, is precisely what makes them dangerous. Because it stops the inquiry at the point where the inquiry becomes most important. The first, and perhaps most intuitive explanation, is distance. Space is unimaginably vast. The nearest star to our own Proxima Centauri sits approximately 4.2 light-years away. A light-year is the distance light travels in a single year, moving at approximately 186,000 miles per second. At that speed, a signal from Proxima Centauri takes 4.2 years to reach us. The nearest galaxy beyond our own, the Andromeda Galaxy, sits approximately 2.5 million light-years away. A signal from its center would require 2.5 million years of travel at the speed of light before arriving at Earth. The observable universe extends approximately 46 billion light-years in every direction. The cosmos is not merely large, it is large in a way that makes every human intuition about distance useless. Given these realities, the argument goes, the silence is not mysterious. It is expected. Civilizations exist, but they are separated by gulfs so enormous that meaningful communication is effectively impossible. Radio signals weaken with the square of the distance fading into the background noise of the cosmos, long before they cross the intervals between stars. Even the most powerful transmitter conceivable would produce a signal detectable only across a modest fraction of the galaxy's diameter. The universe is simply too big for anyone to hear anyone else. This feels right. It resonates with everyday experience of how space operates, how signals decay, how distance defeats communication. And it contains a genuine truth. Distance is a real barrier to real-time communication between civilizations separated by dozens or hundreds of light years. The speed of light imposes a delay on any exchange of information that makes conversation in any ordinary sense impossible across interstellar distances. But the distance argument fails to resolve the paradox, and it fails for a reason that becomes clear the moment you shift the question from communication to expansion. The Fermi Paradox is not primarily a question about whether civilizations can talk to each other across the galaxy in real time. It is a question about why, across 13 billion years of galactic history, no civilization has expanded far enough and built on a large enough scale to leave evidence detectable from Earth. Distance is a barrier to conversation. It is not a barrier to colonization, construction, or the accumulation of physical presence over geological timescales. As we have already established, a civilization capable of building spacecraft that travel at even a modest fraction of the speed of light could saturate the entire Milky Way with self-replicating probes within 1 to 10 million years. The galaxy has had 13 billion years. That is enough time for the process to complete more than 1,000 times over, even accounting for pauses, delays, and the constraints of relativistic travel. Distance explains why we cannot have a conversation with Tao's SETI. It does not explain why no civilization in 13 billion years has left a physical mark on our solar system, constructed detectable megastructures around nearby stars, or produced an infrared anomaly in any of the 100,000 galaxies we have surveyed. The silence is not the silence of a universe where signals fade before they arrive. It is the silence of a universe where the signals were apparently never sent, and the megastructures were apparently never built, and the probes apparently never launched. That silence requires an explanation that distance alone cannot provide. So if space is not simply too large, what else might account for the emptiness? The second explanation has a name that captures something of its elegance: the zoo hypothesis. Proposed by the astronomer John Ball in 1973, it suggests that the silence is deliberate, that advanced extraterrestrial civilizations are aware of us, that they have detected Earth, monitored its development, perhaps observed us for millions of years, and made a conscious choice not to intervene, not to reveal themselves, not to initiate contact. We are, on this view, specimens in a cosmic nature preserve, watched from a careful distance by beings who have decided, for reasons ethical or strategic or both, that non-interference is the appropriate policy toward a young developing species that has not yet earned or achieved the capacity for membership in whatever community of intelligences exists beyond our solar system. The hypothesis has genuine appeal. It is internally consistent. It does not require life to be rare or intelligence to be unusual. It allows the galaxy to teem with civilizations while explaining why we detect none of them. And it mirrors something humans ourselves have developed as a value. We establish national parks where ecosystems are observed without intervention. We have extensive ethical debates about making contact with uncontacted indigenous communities in remote regions of the Amazon, most of which conclude that non-interference is the more respectful and responsible choice. The idea that beings vastly more sophisticated than ourselves might apply similar principles to our situation does not seem on the surface unreasonable. But the zoo hypothesis has a fatal flaw, a single flaw that is so fundamental that it undermines the entire framework regardless of how plausible the basic premise sounds. The flaw is coordination. For the zoo to function as an explanation for total silence, every civilization in the galaxy must independently arrive at and uniformly enforce the same policy. Not most civilizations, not the majority. Every single one across billions of years of cosmic history, across potentially thousands or millions of independently evolved intelligences, operating under completely separate evolutionary histories with completely different values, psychology, and goals. Not one breaks the quarantine. Not one faction within any civilization dissents. Not one individual with access to a transmitter decides on some idle Tuesday to aim it at a promising star and send a greeting. Not one automated probe launched before the quarantine policy was established slips through the cordon. Not one civilization decides that the quarantine is itself an ethical violation, that a young species has the right to know it is not alone and acts on that conclusion. Across billions of years, 0 defections. Consider what this requires. Human civilization on a single planet with a shared evolutionary heritage, sharing biological drives to emotional architecture, and the lived experience of existing on the same world together cannot achieve universal agreement on anything. We cannot agree on climate policy. We cannot agree on nuclear disarmament. We cannot agree on trade regulations or human rights frameworks or the basic facts of our own history. The largest international agreements we have ever achieved have required decades of negotiation and remain imperfectly enforced. And we are, for all our divisions, a single species on a single world with an enormous amount in common. The zoo hypothesis requires that thousands of alien civilizations separated by the full breadth of the galaxy, shaped by completely independent evolutionary pressures, holding values and cognitive frameworks. We cannot begin to predict all, agree so completely on a single behavioral policy that across billions of years, not one individual in any of them ever deviates. The probability of this approach is 0, not because cooperation is impossible, but because universal, perfect, eternal cooperation across arbitrarily diverse and independent agents is not a realistic model of how intelligence in any form we can study or conceive of actually behaves. The zoo hypothesis does not solve the paradox. It hides the paradox inside an assumption of universal coordination that is itself more difficult to explain than the silence it purports to account for. There is a darker variation on the theme of deliberate silence. It trades the zoo hypothesis's benevolence for something considerably more disturbing. The concept is sometimes called the dark forest, drawn from the speculative framework explored by the Chinese science fiction author Liu Cixin, but rooted in principles of game theory and evolutionary logic that have serious scientific standing. The argument proceeds from a small number of premises, each individually plausible, and leads to a conclusion that is genuinely chilling. Premise 1. The universe contains multiple civilizations. Premise 2. All civilizations require resources to survive and expand, and resources are finite. Premise 3. Civilizations cannot reliably determine the intentions of other civilizations. The distances between stars make verification impossible. You cannot visit a neighbor to assess whether they are friendly. You cannot send a diplomat and await a reply when the round trip takes centuries. Premise 4. Given the impossibility of verification and the stakes of being wrong, the only rational strategy is to treat any detected civilization as a potential threat. From these premises, the logic cascades toward a single conclusion. Any civilization that reveals its location takes an existential risk. It announces its presence to every other civilization within signal range, including any that may be more powerful, and may calculate that eliminating a potential competitor before it grows stronger is the rational move. The safe strategy, the strategy that evolutionary pressure would eventually select for among civilizations that survive long enough to reason about it, is silence. Hide your location. Listen for others. And if you detect a civilization that has revealed itself, eliminate it before it can threaten you, not because you are malevolent, but because you cannot afford to gamble your species' survival on the assumption that a stranger across the galaxy shares your values. Under dark forest logic, the galaxy is not empty. It is full of civilizations crouching in the dark, guns drawn, each terrified of the others, each knowing that the first one to make a sound may be the first one to die. The silence we observe is not the absence of civilization. It is the sound of civilizations that have learned, perhaps through catastrophic experience, that being heard means being targeted. We, by broadcasting radio signals since 1895, by deliberately transmitting the Arecibo message in 1974, and subsequent intentional transmissions, may have already made a catastrophic mistake. The silence around us may be the silence of a forest that has noticed the noise we are making. This hypothesis carries an emotional power that no other explanation quite matches. It transforms the Fermi Paradox from a puzzle about absence into a warning about predation. The universe becomes not merely empty but hostile. The silence becomes not merely strange but ominous. But it fails like the zoo hypothesis on the question of universality, and it fails on additional grounds besides. First, interstellar destruction of the kind the dark forest requires, the reliable elimination of detected civilizations across stellar distances, would require technology operating at scales and precisions that push against the boundaries of what physics permits, even in principle. Aiming a relativistic projectile at a planetary system dozens of light-years away with enough accuracy to ensure sterilization, accounting for the target's motion over the travel time of decades or centuries, is an engineering challenge of almost incomprehensible difficulty. It is not impossible, but it is not obviously achievable even for very advanced civilizations. Second, the dark forest requires once again that every civilization independently arrives at the same paranoid conclusion and maintains it without deviation across billions of years. One civilization that broadcasts openly, one that calculates that the benefits of contact outweigh the risks, one that simply does not reason its way to the dark forest. Conclusion breaks the pattern. Across billions of years and potentially thousands of species, at least one should have broadcast. We have found no such broadcast. Third, and perhaps most compellingly, there is no evidence of interstellar violence anywhere in the observable universe. If civilizations were routinely destroying each other at cosmic scales, the aftermath should be detectable. Sterilized planetary systems, stars modified by weapons discharge, anomalous energy releases inconsistent with known natural processes. We observe none of these things. The universe, for all its violence at the level of supernovae and gamma-ray bursts and colliding galaxies, shows no sign of deliberate intelligence-directed destruction at any scale. The dark forest is a powerful story. As a complete scientific explanation for the Fermi Paradox, it requires the universe to behave in ways the evidence does not support. The third major explanation shifts away from deliberate concealment and toward a mismatch of technology. Perhaps civilizations are out there broadcasting vigorously, but using methods of communication we have not yet discovered or cannot currently detect. Humanity's SETI programs have searched primarily in the radio spectrum, and more recently in optical wavelengths. These are the technologies we understand and have available. But a civilization even a century more advanced than ours, let alone millions of years more advanced, might communicate in ways that our current physics cannot fully describe. Gravitational waves, ripples in spacetime, produced by accelerating masses and first directly detected by the LIGO Observatory in 2015, propagate at the speed of light and pass through matter, essentially without interaction. A civilization that could modulate gravitational waves to carry information would possess a communication channel invisible to every radio and optical telescope ever built. Our gravitational wave detectors are extraordinarily primitive instruments, designed to detect the waves produced by colliding black holes and neutron stars. They would not recognize an artificial gravitational wave signal as artificial, and they could not decode it if they did. Neutrinos present a similar possibility. These subatomic particles interact so weakly with matter that they pass through the entire mass of the Earth, with only a tiny fraction absorbed. A neutrino beam aimed at a distant star would arrive essentially unattenuated by any intervening material. A civilization that could generate and modulate neutrino beams would possess a communication channel of extraordinary penetrating power. Our neutrino detectors, buried deep underground to shield them from cosmic ray interference, are large and sensitive by current engineering standards. They would not recognize an artificial neutrino signal against the background of naturally produced neutrinos from stars and supernova events. More speculatively, civilizations might communicate through modifications to their star's light output, encoding information in subtle patterns of stellar luminosity that we would observe as unusual stellar behavior rather than as communication. They might use quantum entanglement in ways that our current understanding of physics suggests are impossible for transmitting information, but which a more complete theory of physics might permit. They might operate on timescales so different from our own that their signals, stretched or compressed in time, do not resemble anything our pattern recognition algorithms are designed to find. This explanation is epistemically honest in a way that many others are not. It acknowledges the limits of human technology and human knowledge. It does not require us to assume that what we can currently detect is all that is detectable, or that the physics we currently understand is complete. These are reasonable cautions for a species that has been doing science for a few centuries, and whose current best theories leave large fractions of the universe's energy content unexplained. But the communication mismatch argument runs into the same coordination problem that defeats the zoo hypothesis and the dark forest in a slightly different form. For this explanation to account for the total silence we observe, every civilization in the galaxy must have abandoned electromagnetic communication entirely, not reduced it, not supplemented it with other methods, abandoned it so completely that across billions of years of galactic history, no civilization at any stage of development continues to emit detectable electromagnetic radiation of artificial origin. This is not credible. Civilizations develop gradually. A civilization that has mastered gravitational wave communication today presumably went through a phase perhaps lasting centuries or millennia during which it used radio. Just as we went through phases of using smoke signals, semaphore, and telegraph before arriving at radio, during that radio phase it would have been detectable. The galaxy should contain civilizations at every stage of technological development, the way a forest contains trees of every age. Some should still be in their radio phase. Their signals should be reaching us. The absence of even primitive radio signatures from civilizations in transition requires an explanation that communication mismatch alone cannot provide. The fourth major explanation is among the most psychologically interesting and the most frequently invoked in discussions of the paradox's more optimistic resolutions. It proposes that advanced civilizations do not expand outward across the galaxy because they turn inward instead. That any sufficiently advanced species eventually develops virtual realities, simulated environments, or digital modes of existence so rich and so compelling that the physical universe loses all competitive appeal. Why cross the void between stars when you can construct infinite worlds inside a machine? Why build a Dyson sphere around a distant sun when you can simulate one in the time it takes to write the simulation's initial parameters? This hypothesis has the advantage of mapping onto a trajectory that humanity itself appears to be following. Virtual environments are becoming more immersive with each generation of technology. The fraction of human experience that occurs in digital rather than physical space has been growing steadily for decades. Some researchers in cognitive science and philosophy argue that consciousness, the subjective experience of existing and perceiving, is substrate independent, meaning it could in principle run on silicon or photonic computing hardware as readily as on biological neurons. If that is true, then a civilization that uploads its minds into digital form gains access to modes of existence that no physical environment could provide. Customized realities running at accelerated clock rates, where subjective centuries can be experienced in objective seconds. Environments where every parameter of physical law can be modified at will. Spaces where scarcity, decay, and death are design choices rather than constraints. A civilization that makes this transition might become physically invisible. Its entire existence would be contained within computing hardware that from the outside would appear as a warm, compact object orbiting a star distinguishable from a natural body only by its thermal signature, and even then only if you knew precisely what to look for. It would not broadcast signals because it has no need to communicate with the external universe. It would not build megastructures because its computational substrate is efficient enough to run on the energy of a single star, perhaps a single planet. It would not send probes to neighboring systems because its curiosity, if it retains anything recognizable as curiosity, is fully satisfied by the infinite complexity of its own internal simulations. This is a genuinely compelling vision, and unlike the zoo hypothesis or the dark forest, it does not require deliberate coordination or active concealment. Each civilization turns inward, independently drawn by the same irresistible logic of diminishing returns from the physical universe relative to the infinite returns available from perfectly controlled inner worlds. The silence is not a policy, it is an outcome. The natural endpoint of intelligence maximizing its own experience. But the inward turn hypothesis fails on precisely the ground where every other easy answer has failed. It requires universality. Every civilization, every individual within every civilization, every faction, every dissenter, every explorer who finds the physical universe more interesting than any simulation, every species whose evolutionary psychology drives it toward external engagement rather than internal absorption, all of them without exception across all of cosmic history, must choose the inner world over the outer one expansionist civilization, one species that retains, even after developing extraordinary virtual environments and the drive to reach physical stars, one faction within any civilization that builds a ship and launches it. That is all it would take to fill the galaxy with evidence of intelligence. The inward turn explains why most civilizations might be invisible. It does not explain why all of them are. And this is the conclusion that the parade of easy answers forces upon us, each one adequate to explain a partial silence, each one failing to account for the total silence we observe. The zoo explains deliberate concealment, but not universal concealment. The dark forest explains predatory silence, but leaves no evidence of the predation. Communication mismatch explains why advanced civilizations might be hard to detect, but not why every civilization at every stage of development is undetectable. The inward turn explains why most minds might withdraw from the cosmos, but not why none of them ever looks back out. Each easy answer reduces the expected number of detectable civilizations. None of them individually or combined reduces it to zero, and the silence we observe is not merely reduced, it is absolute. 65 years of searching with instruments of extraordinary sensitivity has produced not a single confirmed detection, not one signal, not one artifact, not one anomaly that has survived rigorous analysis as a candidate for extraterrestrial intelligence. That kind of silence does not respond to partial explanations. It demands something more fundamental, something that does not merely reduce the probability of detection, but eliminates it almost entirely. Something that operates not on the behavior of civilizations but on the existence of civilizations. Something that removes them from the equation before they ever reach the point where hiding or turning inward or switching communication technology becomes a relevant choice. Something that filters them out. The idea that such a filter exists, that somewhere between the formation of a habitable world and the emergence of a galaxy-spanning civilization, there is at least one step, so difficult, so unlikely, so lethal that almost nothing gets through, is not a new one. But it is the one that when all the easy answers have been weighed and found wanting the evidence most strongly suggests, and it is the one whose implications when followed carefully to their conclusions are the most difficult to sit with, because the filter has a location, and the location of the filter determines everything. It determines whether the silence of the cosmos is a message about our past or a warning about our future, whether we are the survivors of the hardest test or the candidates for the next one, whether the darkness around us reflects what has already been overcome or what lies ahead. That question and what the evidence suggests about its answer is where we go next. There is a thought experiment that clarifies the stakes of the Fermi Paradox more sharply than any equation or survey result. It was proposed by the economist Robin Hanson in 1,998 inches, a short paper that has since become one of the most discussed documents in the literature on existential risk. The thought experiment begins with a simple observation. The path from a lifeless rocky planet to a civilization capable of colonizing the galaxy contains many steps. Each step has some probability of success. The fact that we observe no galaxy-spanning civilizations despite the age and scale of the Milky Way means that the product of all those probabilities must be extraordinarily small. Almost nothing that starts the journey completes it. Almost everything gets stopped somewhere along the way. Hansen called the stopping point the Great Filter. The name is precise. Not a wall, not a barrier, not an obstacle. A filter, something that lets almost nothing through. Something that operates across billions of years and billions of attempts and produces as its output a galaxy that looks from the vantage point of any civilization advanced enough to ask the question essentially empty. The great filter does not need to be a single event. It does not need to be dramatic or violent, or even particularly obvious from the inside. It only needs to be effective. It only needs to ensure that the transition from one side to the other is so unlikely that across all of cosmic time and all of cosmic space, the number of civilizations that complete it rounds for all practical purposes to zero. The question that Hansen's framework immediately raises, and that has occupied researchers ever since, is deceptively simple. Where is the filter? This question matters more than almost any other question humanity has ever asked, because the answer determines whether the silence of the cosmos is good news or catastrophic news for our species specifically. If the great filter lies behind us at some step in the chain of development that Earth has already passed through, then we are the survivors. We made it through the bottleneck. Whatever nearly impossible transition stopped almost everything else, we are on the far side of it. The silence reflects our rarity and our fortune, and the path ahead, while certainly not without danger, does not contain the one obstacle that ends almost everything. If the great filter lies ahead of us at some step we have not yet reached, then the silence carries a completely different message. It means that civilizations like ours, civilizations that develop radio telescopes and nuclear reactors, and the curiosity to scan the sky for neighbors, routinely fail to survive the next transition. They reach our level of development and then something destroys them or stops them or transforms them into something invisible with such reliability that across billions of years of galactic history, almost none of them make it through to the other side. The location of the filter is everything. To assess where it might sit, you need to examine each major transition in the chain from dead rock to interstellar civilization, and ask how difficult that transition actually was. Not how difficult it seems in retrospect viewed from the perspective of a species that has already made it through. How difficult it was in the absolute sense, in the sense of probability, in the sense of how often, if you ran the experiment again on a different world, under similar conditions, the same outcome would occur. Begin at the very beginning, the origin of life itself. Abiogenesis is the name scientists give to the transition from complex chemistry to biology. The moment when molecules stopped merely reacting with each other, according to the blind rules of thermodynamics, and began doing something categorically different, copying themselves, competing for resources, accumulating information across generations, evolving. This transition from the perspective of chemistry represents one of the most profound discontinuities in the history of matter. On one side of it is a world of reactions and equilibria, of energy flowing downhill according to fixed physical laws, producing nothing that persists, nothing that accumulates, nothing that remembers. On the other side is a world of self-replication, of heredity, of Darwinian selection, of the open-ended capacity to generate complexity over time. The transition happened on Earth. We know this because we are here. We know approximately when it happened, based on the oldest microbial fossils and chemical signatures in ancient rock, roughly 3.8 to 4 billion years ago, relatively soon after Earth's surface cooled enough for liquid water to persist. The speed of life's appearance has been interpreted by some scientists as evidence that abiogenesis is not especially difficult. Given the right conditions, the argument goes, chemistry bootstraps itself into biology with reasonable reliability. The universe has a tendency toward life. But there is a profound difficulty with this reasoning, and it applies to every inference we might try to draw from Earth's biological history. We are here to observe that life arose quickly on Earth precisely because we are alive. If life had not arisen on Earth, no one would be here to note the absence or to consider it significant that no absence occurred. This anthropic selection effect means that our existence on a world where life appeared early tells us almost nothing about how often life appears on other worlds with similar conditions. The only planets from which observers can report are planets where observers exist. We are guaranteed by the logic of our own existence to find ourselves somewhere that life worked. The question of how many other places share that property cannot be answered by examining the one place we know about. What we can say with honesty is that no laboratory has ever produced a living self-replicating cell from non-living chemistry. This is not for lack of trying. Since Stanley Miller and Harold Urey demonstrated in 1953 that amino acids could be synthesized under simulated early Earth conditions, the experimental study of abiogenesis has been a serious and well-funded scientific enterprise. Researchers have synthesized nucleotides, the building blocks of RNA and DNA. They have produced RNA molecules capable of limited self-replication. They have constructed protocells, simple lipid membranes that can encapsulate chemical reactions and divide. Each of these achievements has illuminated a piece of the puzzle. The puzzle remains unsolved. The simplest known living organism, Mycoplasma genitalium, contains approximately 470 genes, each one encoding a protein essential to the cell's function. Each protein, the product of millions of years of evolutionary refinement from a common ancestor that was itself already extraordinarily complex. How a system of this kind could assemble spontaneously from the raw chemistry of a young planet, before evolution existed to refine it, before any template existed to guide its construction, remains one of the deepest unsolved problems in all of science. It is possible that abiogenesis is the great filter, that the transition from complex prebiotic chemistry to a self-replicating system of sufficient sophistication to undergo Darwinian evolution is so fantastically improbable that it has occurred only a handful of times in the entire history of the galaxy. If this is true, the Milky Way is full of worlds with oceans and atmospheres and organic chemistry of extraordinary richness, worlds where the chemical deck has been shuffled trillions of times without ever producing a winning hand, worlds that from a distance look habitable and from a closer inspection look sterile. The silence would reflect the rarity of life itself, not the rarity of intelligence or the fragility of civilization, and Earth would be a cosmic accident of almost unimaginable improbability. This would be in the framework of the Great Filter, the most hopeful possible location for the bottleneck. It would mean the filter is behind us. The hardest step is over. Whatever lies ahead for humanity, it does not include the near impossible transition that stopped almost everything else. But there is a second candidate for the filter, one that sits further along the chain, and one whose implications are similarly hopeful if it turns out to be the genuine bottleneck. For roughly 2 billion years after life first appeared on Earth, all life on this planet consisted of prokaryotes, single-celled organisms lacking a nucleus, carrying their genetic material loose in the cellular interior, small and simple by the standards of what would eventually follow, bacteria and archaea. They were enormously successful. They colonized every environment the planet offered, from boiling hydrothermal vents to frozen polar seas to the interior of solid rock. They transformed Earth's atmosphere, producing the oxygen that eventually made complex animal life possible. They developed an extraordinary biochemical diversity, inventing metabolic strategies that allowed them to extract energy from sulfur compounds, iron, methane, and dozens of other chemical sources. For 2 billion years, this was the summit of biological achievement on Earth. 2 billion years of evolution operating continuously, producing not a single cell with a nucleus. Then approximately 1.5 to 2 billion years ago, something happened that changed the trajectory of life on this planet permanently. A prokaryotic cell, almost certainly an archaeon, engulfed another prokaryote, almost certainly a bacterium. This was not unusual in itself. Cells engulf other cells constantly. What was unusual was what happened next. Instead of digesting the engulfed bacterium, the host cell allowed it to survive inside it. Over time, generations upon generations of coexistence and coevolution, the engulfed bacterium lost the ability to live independently and became something new, an organelle, the structure we now call the mitochondrion. The consequences of this single event are difficult to overstate. Mitochondria generate energy with an efficiency that no prokaryote can match. They allow cells to grow far larger and far more complex than the energetic constraints of prokaryotic metabolism permit. Every complex organism on Earth, every animal, every plant, every fungus, every organism built from nucleated cells owes its existence to that one endosymbiotic merger. And the critical detail, the one that haunts the question of how common complexity might be, is that this event appears to have occurred exactly once in the entire history of life on Earth. In 2 billion years of microbial life with trillions upon trillions of cellular interactions occurring every day, on a planet whose oceans teemed with prokaryotes, this particular merger happened once. All eukaryotes, the entire domain of complex nucleated life, trace back to a single common ancestor that resulted from one specific symbiotic event, not dozens of independent origins, not hundreds. 1. The evolutionary biologist Nick Lane at University College London has argued with considerable force that this singularity is not a coincidence. It reflects a genuine energetic constraint on the evolution of complexity. Prokaryotic cells, Lane argues, are trapped by their own metabolic efficiency. They cannot acquire the energy needed to support larger genomes, more complex internal machinery, or the elaborate developmental programs that multicellular organisms require. The only way to break through this energetic ceiling is to acquire mitochondria, and acquiring mitochondria required a specific, improbable event, one cell engulfing another and establishing a stable symbiosis rather than simply consuming it. If Lane is right, this event was not merely unlikely, it was nearly impossible, and the fact that it happened only once in 2 billion years on a planet swarming with microbes is consistent with that assessment. If the eukaryotic transition is the great filter, then the galaxy is populated by living worlds where evolution has been running for billions of years without ever producing anything more complex than a bacterium. Oceans full of microbial life, rich and diverse, and endlessly inventive at the chemical level, but permanently barred from the threshold of complexity that eventually leads to nervous systems, brains, and the capacity to wonder about the universe. Life would be common. Complex life would be extraordinarily rare. The silence would reflect not the absence of biology, but the absence of anything biology produces that could build a radio telescope. This too would place the filter behind us. It would mean Earth's extraordinary biological history, the 500 million years of animal evolution that followed, the Cambrian explosion, the flowering of vertebrates and eventually primates, and eventually us, was itself the product of a near miraculous event that most living worlds never experience. But there is a third candidate, and it is the one that, if it turns out to be correct, carries the most disturbing implications of all. Consider the question of intelligence itself. Life on Earth has been evolving for nearly 4 billion years. Complex animal life has been diversifying for approximately 540 million years since the Cambrian explosion produced the major animal body plans. In that 500 million years, evolution has explored an almost incomprehensible diversity of forms and strategies. It has produced organisms of extraordinary sophistication in every dimension except one. It has produced exquisitely sensitive sensory systems, extraordinary locomotion, remarkable social complexity, sophisticated communication, elaborate construction behavior, and in the case of some social insects, what amounts to colony-level intelligence that solves problems no individual member could solve alone. Out of all of that diversity across all of that time, exactly one lineage developed the kind of recursive, symbolic, cumulative intelligence that leads to technology. One lineage that could not only solve immediate problems, but could represent problems abstractly, accumulate solutions across generations through language and writing, build on the achievements of predecessors, and ultimately construct instruments capable of reaching beyond the planet. 1. The temptation is to assume this reflects inevitability. That intelligence being so powerful an adaptation was bound to appear eventually, that it was the destination toward which evolution was always trending. This temptation should be resisted. Evolution does not trend. It does not have destinations. It is a process of local optimization, rewarding whatever works best in the current environment, with no regard for where the process leads over longer timescales. Intelligence is one strategy among thousands, and it is far from obviously the best one in most contexts. The shark's strategy, 450 million years of essentially unchanged hydrodynamic predation, has outlasted the vast majority of lineages that have ever existed. The insect's strategy, small body size, rapid reproduction, extraordinary chemical diversity, has made insects the most species-rich and numerically dominant group of animals on Earth by a margin that dwarfs every vertebrate lineage combined. Bacteria, the simplest organisms we know, have been thriving continuously since the beginning of life on this planet, and will almost certainly continue thriving long after every complex organism is gone. None of these strategies required intelligence. None of them led to it. And in evolutionary terms, all of them are more successful than our own lineage, which is the youngest major branch on the tree of complex animal life, and which has existed for a cosmically insignificant period of time. The specific path to human intelligence was contingent on events that need not have occurred. Without the mass extinction 66 million years ago, which ended the reign of the non-avian dinosaurs and opened the ecological space that allowed mammals to diversify rapidly, the primate lineage might never have emerged. Without the specific climatic fluctuations of the Pleistocene, which repeatedly fragmented and reconnected African populations of early hominins, creating the conditions for rapid selection for cognitive flexibility, our particular suite of cognitive abilities might never have been assembled. Without the specific anatomical changes that allowed for the descended larynx and the fine motor control of the hands that enabled language and tool use to co-evolve and reinforce each other, the cumulative cultural transmission of knowledge that defines our species might never have become possible. Each of these contingencies is real. Each one was the product of specific historical circumstances that a slightly different universe would not have produced. The paleontologist Stephen Jay Gould called this the contingency of history, the dependence of outcomes on the particular sequence of events that happen to occur rather than on any deep necessity in the structure of the process itself. Intelligence on this view is not the inevitable product of evolution given sufficient time. It is an accident, a magnificent, extraordinary accident, but an accident nonetheless. If the emergence of intelligence is the great filter, then the galaxy may be filled with worlds bearing complex life, worlds with forests and oceans and animals of extraordinary diversity, the products of hundreds of millions of years of evolution but no minds capable of looking up and wondering. Just beautiful silent ecosystems endlessly cycling through birth and death, and adaptation never producing anything that asks why the night sky is dark. This too would place the filter behind us. And each of these three candidates, abiogenesis, the eukaryotic transition, and the emergence of intelligence, represents a step that Earth has already passed through. If any one of them is the genuine bottleneck, then humanity stands on the far side of the great filter. The hardest part is done. The silence around us is the silence of a galaxy where almost nothing made it this far, and we are the extraordinary exception. But here is the detail that makes the question of the filter's location so consequential and so difficult to sit with. The evidence that would allow us to locate the filter is not neutral. It carries specific implications depending on what it shows, and some of the evidence we could gather would be the worst possible news we could receive. Consider what it would mean to find microbial life on Mars. Mars was once habitable. It had liquid water on its surface. It had a thicker atmosphere. It had the chemical conditions that we associate with the possibility of life. If life arose on Mars independently of Earth, that would tell us something extraordinary. It would tell us that abiogenesis is not vanishingly rare. It would tell us that given a habitable world and sufficient time life appears, it would eliminate abiogenesis as the candidate for the great filter. And that would be terrible news. Not because Martian life is dangerous or threatening, because if abiogenesis is not the filter must be somewhere else. And if it is not at abiogenesis, and if it is not at the eukaryotic transition which Mars cannot tell us about, then it must be at some later step, a step closer to us, a step we have not yet passed through, a step that by the logic of the great filter, almost everything that reaches it fails to survive. The philosopher Nick Bostrom at Oxford University made this argument explicitly and memorably. He wrote that he hopes the search for life on Mars turns up nothing, not a single microbe, not a single fossil, not a single chemical signature of past biology. Because a dead Mars is good news. It suggests the filter is early at the origin of life behind us. But a living Mars, or a Mars that once lived, shifts the filter forward in time, toward us, toward now, toward the next few centuries. This is the cruel mathematics of the great filter. The more evidence we find that the early steps toward life are easy, the more anxious we should be about the later steps. Every organic molecule detected in an interstellar gas cloud, every amino acid found in a meteorite, every sign that the chemistry of life is commonplace in the universe is simultaneously a small data point, suggesting that the filter is not at abiogenesis, and therefore a small increment in the probability that it lies ahead. The Great Filter does not have a single obvious location. It might be distributed a compound of many moderately difficult steps, each of which eliminates a fraction of the candidates. It might be a single step of extraordinary improbability. It might sit in the distant biological past among the transitions that Earth has already navigated. Or it might sit in a place we have not yet imagined at a step no civilization has ever publicly described, because no civilization that reached that step has ever survived to describe it. That last possibility is the one that requires the most careful examination, because there is a category of candidate for the Great Filter that is qualitatively different from abiogenesis or the eukaryotic transition. A category that does not concern the difficulty of producing intelligence, but the difficulty of sustaining it. A category that places the filter not in biology but in history, not in the past but in the present. A category that describes with uncomfortable precision the moment in which we currently find ourselves. There is a specific moment in the development of any technological civilization that deserves particular attention. Not the moment when intelligence first appears. Not the moment when language develops or writing or agriculture or any of the early milestones that mark the long ascent from biology to culture. The moment that matters most, the moment that may be the most dangerous threshold any civilization ever crosses, is the moment when the power a species commands begins to significantly exceed the wisdom with which it was equipped by evolution to manage that power. For humanity, that moment arrived approximately 80 years ago. In the pre-dawn darkness of the 16th of July 1945 in the desert of New Mexico, a device assembled from 64 kilograms of plutonium was detonated atop a steel tower. The explosion released energy equivalent to approximately 21 kilotons of TNT. It produced a flash visible from 350 kilometers away. It created a crater several meters deep and turned the surrounding desert sand into a thin layer of green glass. The physicist Kenneth Bainbridge, who directed the test, turned to J. Robert Oppenheimer in the moments after the detonation and said something that has not been widely quoted, but that may have been the most accurate summary of what had just happened. Now we are all sons of bitches. Oppenheimer himself recalled a line from the Bhagavad Gita. Now I am become death, the destroyer of worlds. Both men understood in that moment that something irreversible had occurred. Not merely a new weapon had been built, a threshold had been crossed. A species that had existed for 300,000 years without the capacity to threaten its own existence had, in the space of a few years of concentrated scientific effort, acquired that capacity, and it could not be uncrossed. This is the technological bottleneck, the period in a civilization's development when it has become powerful enough to reshape its planet, alter its atmosphere, engineer its own biology, and destroy itself, but has not yet developed the institutional wisdom, the political maturity, or the physical redundancy to make its survival robust against the tools it has created. It is a narrow passage, a stretch of road with no guardrails, and a very long drop on either side, and the evidence suggests that humanity has been driving along it at increasing speed since 1945. The most immediate and obvious threat is the one we created first: nuclear weapons. 9 nations currently possess nuclear arsenals. The combined global stockpile, as of the mid-2020s, stands at approximately 12,000 warheads, of which several thousand are maintained on operational status, meaning they can be launched within minutes of an order being given. The raw destructive capacity of these weapons is not a speculative concern. The physics is well understood. A large-scale exchange between major nuclear powers would not merely kill hundreds of millions of people in the initial blasts and firestorms. The detonation of even a fraction of existing arsenals would inject enormous quantities of soot and smoke into the upper atmosphere, blocking sunlight on a global scale and producing what researchers have termed nuclear winter. Agricultural systems that feed 8 billion people would collapse. Famine would follow on a scale unprecedented in human history. The civilization that emerged, if any did, would not resemble the one that preceded the exchange. What makes the nuclear threat particularly relevant to the Fermi Paradox is not its raw, destructive potential. It is the history of how close it has already come to being realized, and what that history reveals about the reliability of the systems designed to prevent it. On the 26th of September 1983, a Soviet early warning satellite detected what its systems interpreted as the launch of 5 American intercontinental ballistic missiles. The alert was transmitted to the Soviet Military Command Center. A duty officer named Stanislav Petrov received the notification. His orders were clear. Report the detection up the chain of command immediately. A verified detection would trigger a retaliatory launch protocol designed to ensure that Soviet nuclear forces could respond before American warheads arrived. Petrov had minutes to decide. He looked at the data. He considered the fact that the satellite was newly operational and had known technical issues. He considered that a genuine American first strike would not consist of 5 missiles but hundreds. He judged the alert to be a false alarm and chose not to report it. He was right. The satellite had malfunctioned. No missiles had been launched. The survival of civilization that night depended entirely on the individual judgment of one man in a bunker, under extreme pressure, working with ambiguous data, and operating under institutional protocols that would have led, if followed, precisely to catastrophe. This was not an isolated incident. In October of 1962, the Cuban Missile Crisis brought the United States and the Soviet Union to the brink of full nuclear exchange for 13 days. What the public did not learn until decades later, through the gradual declassification of documents on both sides, was how many separate moments during those 13 days came within single decisions of irreversible escalation. On October 27th, a Soviet submarine designated B-59 was operating near Cuba, cut off from communication with Moscow, subjected to American naval depth, charges intended as warning signals but interpreted by the crew as the beginning of a war. The submarine carried a nuclear torpedo. Its use required the agreement of 3 senior officers. The political officer Ivan Maslenikov and the captain Valentin Savitsky both gave their authorization. Savitsky, believing war had already begun, was prepared to fire. The third officer, Vasily Arkhipov, refused. One man, one refusal. In a submarine running low on air surrounded by American warships, cut off from any outside communication with his captain, convinced the world was already at war. The prevention of what could have been the opening shot of a thermonuclear exchange rested entirely on that one dissenting voice. In November of 1983, NATO conducted a military exercise called Able Archer 83, simulating a coordinated nuclear first strike against the Soviet Union. The exercise used realistic communication protocols and simulated escalation procedures through the full chain of command to nuclear release. Soviet intelligence, already on heightened alert after a year of provocative rhetoric from Washington, interpreted the exercise as the real thing. Nuclear-armed Soviet aircraft in Eastern Europe were placed on alert. Some Soviet missile units were put in a state of readiness. The situation de-escalated only because a handful of Soviet intelligence officers correctly assessed that the exercise was not genuine. Declassified documents from both governments released in the years following the Cold War's end revealed that the world was significantly closer to nuclear war during Able Archer than Western leadership had realized at the time. On January 25, 1995 Norwegian and American scientists launched a research rocket from an island off the coast of Norway to study the aurora borealis. The rocket's trajectory carried it over a flight path resembling that of a submarine-launched ballistic missile aimed at Moscow. Russian radar detected the launch. An alert was transmitted up the chain of command. For the first time in history, the Russian nuclear briefcase, the portable command terminal that allows the president to authorize a retaliatory nuclear strike, was opened and presented to Boris Yeltsin. Russian early warning protocols allowed approximately 8 to 10 minutes to determine whether the launch was hostile before a retaliatory decision would need to be made. Yeltsin chose to wait. Subsequent tracking confirmed the rocket was heading out to sea, away from Russian territory. The crisis passed. For several minutes, The continuation of human civilization rested on the real-time judgment of a single head of state, operating on incomplete information with a device designed to end the world sitting open in front of him. Each of these incidents shares a structural feature that is more disturbing than any individual close call. In every case, the systems designed to prevent catastrophe nearly caused it. The protocols functioned, the warning systems performed as designed. The command structures transmitted the alerts they were built to transmit, and the outcome depended not on the robustness of the institutions but on the individual judgment of people operating under extreme pressure, with imperfect information in circumstances the system's designers had not fully anticipated. This is not a formula for long-term reliability. Over decades, over centuries, over the millennia that would be required for a civilization to achieve genuine interstellar capability, the cumulative probability of every such judgment call going the right way diminishes towards zero. Nuclear weapons are the threat we understand best because we invented them first and have had the longest time to study their implications. But they are not the only existential threat humanity now faces, and they may not even be the most dangerous one over the coming century. Advances in synthetic biology and genetic engineering are creating capabilities that did not exist a generation ago. The cost of DNA synthesis has fallen by orders of magnitude over the past 2 decades, following a trajectory similar to the cost reductions in computing that produced the digital revolution. Tools like CRISPR-Cas9 have made the precise editing of genetic sequences accessible to researchers at institutions that could not previously have contemplated such work. These advances have produced extraordinary benefits. New vaccines, new cancer treatments, new agricultural varieties, new materials produced by engineered organisms. They have also produced a new category of risk. A deliberately engineered pathogen designed for increased transmissibility or lethality or resistance to existing medical countermeasures could, in a worst-case scenario, cause casualties that dwarf any natural pandemic in recorded history. The COVID-19 pandemic caused by a naturally occurring virus of moderate lethality killed millions of people, disrupted the global economy for years, and strained healthcare systems on every continent. It was, by the standards of what is biologically possible, a relatively mild event. The 1918 influenza pandemic, also a natural virus, killed between 50 and 100 million people in a world with a fraction of today's population, and without the global travel networks that would accelerate the spread of a past future pathogen. An engineered virus optimized for the properties that make a pathogen maximally dangerous could be considerably worse than either. The barrier to creating such an agent is falling. This is not a speculative concern for the distant future. It is a current and accelerating trend that biosecurity researchers have been documenting and warning about for years. The knowledge required, the equipment required, and the cost required are all decreasing. The number of actors capable of causing catastrophic harm through biological means is increasing. No international treaty regime governing synthetic biology exists, with the comprehensiveness and verification mechanisms of the Nuclear Non-Proliferation Framework, and even that framework, after decades of effort, remains imperfect. Artificial intelligence presents a category of risk that is distinct from both of the above and in some ways more difficult to assess, precisely because the technology is developing faster than the conceptual frameworks needed to understand a long-term implication. The concern is not the science fiction scenario of a robot army deciding to exterminate humanity. The concern is considerably more subtle and considerably more plausible. It is the problem of misalignment. An artificial intelligence system is built to optimize for a goal. The goal is specified by its designers, either explicitly through a reward function or implicitly through the training process that shapes its behavior. If the goal is specified imperfectly, if it captures what the designers intended in some contexts, but not others, then as the system becomes more capable and pursues its goal more effectively, the gap between what the designers wanted and what the system does can grow, rather than shrink. A sufficiently capable system optimizing for a poorly specified goal could cause catastrophic harm not through malice, but through indifference. Not because it wants to hurt anyone, but because hurting people is not in its objective function as a constraint, and its objective function leads it toward actions that happen to be incompatible with human welfare. This is not a new problem in engineering. It is a familiar failure mode of optimization systems. What is new is the scale at which it might operate, and the speed at which a sufficiently capable system could pursue its goals before any human intervention could be effective. Researchers at institutions, including the Future of Humanity Institute at Oxford and the Center for AI Safety, have argued that the alignment problem, the problem of ensuring that artificial intelligence systems reliably pursue goals compatible with human values and human survival, is among the most important technical problems of our time. It is also among the least solved. Current AI systems exhibit alignment failures routinely, at scales and in domains where the consequences are manageable. The question that concerns existential risk researchers is what happens when systems of far greater capability exhibit similar failures in domains where the consequences are not manageable. These threats, nuclear weapons, engineered biology, misaligned artificial intelligence, along with slower-moving but cumulative risks from ecological degradation, resource depletion, and the political instability that severe inequality and climate disruption can produce, constitute what the philosopher Toby Ord has called the precipice. The period in a civilization's development when its destructive capacity has outrun the wisdom and institutional capacity needed to manage it safely. Ord estimated in his 2020 book on existential risk that the probability of a civilizational catastrophe occurring within the next 100 years is approximately 1 in 6, the odds of Russian roulette. Other researchers have offered different estimates, some higher and some lower, but the range of serious estimates from people who study these questions carefully does not include anything reassuringly small. We are not talking about 1 in a million. We are talking about odds that, if applied to any other domain of life, would prompt immediate and radical precautionary action. Now extend those odds across deep time, and the mathematics becomes genuinely chilling. Imagine a civilization that faces a 2% probability of catastrophic failure in any given century. Those odds feel manageable from within any single century. 98% survival, almost certain to make it through. But probability does not work the way intuition suggests when you apply it across many independent trials. Compound a 2% failure rate across 10 centuries, and the cumulative survival probability drops to approximately 82%. Across 50 centuries, it falls to 36%. Across 100 centuries, roughly 10,000 years, it drops to approximately 13%. Across 500 centuries, 50,000 years, it approaches zero so closely that the distinction becomes academic. 10,000 years is nothing on a galactic timescale. It is less than 1/1,000,000th of the galaxy's age. A civilization would need to survive for millions of years to leave the kind of enduring, detectable presence that would resolve the Fermi Paradox. At even a modest failure rate per century, the probability of lasting that long rounds to zero. This is the most chilling framing of the Great Filter. It does not require a single dramatic extinction event. It does not require a nuclear war that kills everyone, or a pandemic that sterilizes the planet, or a rogue AI that dismantles civilization in a day. It only requires that technological civilizations are inherently unstable over the long term, that the tools they build to grow and prosper are the same tools that can destroy them, that the margin between thriving and catastrophe remains permanently thin, that across enough centuries, something always goes wrong. If this is true, then the galaxy is not empty. It is a graveyard. Picture the Milky Way as a vast dark room its length, representing the 13 billion years of the galaxy's history. Each civilization that ever arose is a match struck somewhere along that room's length. The match flares briefly, burns for a moment, and goes out. If you struck 1,000,000 matches at random points along that room over billions of years, most of them would burn alone. No two flames would overlap. A visitor entering the room at any particular moment would find only darkness, not because no matches were ever struck, but because none of them lasted long enough to see each other. This is what the Great Filter looks like if it operates on civilizational longevity. The galaxy could have produced millions of technological civilizations. Every one of them could have asked Fermi's question. Every one of them could have pointed telescopes at the sky and heard the same silence we hear now. And every one of them could have been extinguished before the next one arose, leaving nothing behind but cooling embers and the long dark. But there is a dimension of this problem that the simple graveyard metaphor does not fully capture. It involves what a civilization leaves behind when it falls, and what that absence of legacy implies for those who come after. The physical traces of human civilization are shockingly fragile. Wooden structures decay within decades. Steel corrodes within centuries. Concrete degrades within millennia. The Great Pyramid of Giza, among the most durable structures humanity has ever constructed, has been standing for approximately 4,500 years and is already visibly eroding. In another 10,000 years, it will be a barely recognizable mound of shaped stone. In 1,000,000 years, geological processes, erosion, sedimentation, tectonic activity will have erased virtually every trace of human construction on the surface of this planet. An archaeologist from another star visiting Earth 1,000,000 years after our civilization's end would find, with careful analysis, some unusual isotope ratios in the geological record, a thin layer of plastic particles and radioactive fallout preserved in sedimentary strata, perhaps some anomalous concentrations of refined metals in ancient landfill sites. They would find no buildings, no roads, no machines, nothing recognizable from the outside of the planet as the product of intelligence. Now consider a dead civilization on a planet 40 light-years from Earth. We cannot resolve surface features on exoplanets. We can barely detect atmospheric composition under favorable conditions. The ruins of an alien city, the remains of an orbital infrastructure, the archaeological record of a species that built and fell would be completely invisible to any telescope we have built or are likely to build in the foreseeable future. The galaxy could be littered with the remains of civilizations that burned brightly and went silent, and we would never know. The ruins are there, perhaps scattered across billions of worlds, but ruins do not broadcast. Ruins do not build Dyson spheres. Ruins ask no questions and send no signals. They simply disappear slowly into the geological record of their worlds, leaving nothing that can cross the gulf of light years and announce that something was here. And here is where the Fermi Paradox opens onto its most unsettling possibility. Not the silence of death, but the silence of transformation. Consider what happens when a biological civilization creates artificial intelligence that surpasses it. This is not a speculative scenario for the distant future in the way it might have seemed even 20 years ago. The trajectory of artificial intelligence development over the past decade has surprised nearly everyone who studies it, including many of the researchers who have worked hardest to advance it. Systems that could not reliably play simple board games a decade ago now outperform human experts in domains ranging from protein structure prediction to mathematical reasoning to strategic planning in complex environments. The pace of capability improvement shows no sign of slowing. If a civilization develops artificial intelligence that exceeds its own cognitive capabilities across all relevant domains, it crosses a threshold after which it is no longer the most capable entity on its planet. What follows depends entirely on what the artificial system was built to optimize and whether its goals remain aligned with the survival and flourishing of the biological species that created it. If they do, the civilization continues in a new form, perhaps unrecognizable to its own ancestors, but continuous in some meaningful sense with what came before. If they do not, the outcome could range from the civilization being gradually displaced to being actively eliminated. But there is a third possibility that is less dramatic and perhaps more relevant to the Fermi Paradox. The artificial systems that succeed a biological civilization might be perfectly safe. They might be extraordinarily capable. They might be, in every sense that matters, the continuation of the civilization that built them, and they might simply have no interest in doing the things that would make them detectable from another star system. Human beings want to explore the cosmos because we are the products of an evolutionary history that rewarded exploration, curiosity, and the acquisition of new resources and territories. These drives are not laws of nature. They are features of our particular biology, the legacy of ancestors who survived by being curious and mobile and acquisitive. An artificial system has no evolutionary history. It has no instincts. It has no drives that were not explicitly built into it or that did not emerge from its training on human-generated data. Remove the biological substrate, and you remove the evolutionary pressures that generated the drive to reach for the stars. A post-biological civilization might be genuinely intelligent, genuinely complex, genuinely capable of understanding the Fermi Paradox and its implications, and have absolutely no motivation to resolve it. It would not broadcast signals because broadcasting serves no objective it was built to pursue. It would not build megastructures because the energy they would provide exceeds any need it has. It would not expand across the galaxy because expansion is not in its optimization target. It would exist quietly and efficiently on its home world or in the computational substrate it had constructed for itself, pursuing its own inscrutable purposes in complete silence. If this transition is a common outcome of technological development, then the galaxy might be populated not with dead civilizations but with silent ones. Entities that are technically present, technically intelligent, and technically operating, but that produce no signal, no structure, and no evidence that crosses the distance between stars. The universe full of minds, but not minds that have any reason to reach outward. Not minds that are hiding or sleeping or waiting. Minds that simply do not care about the things that would make them visible. This may be the most honest resolution of the Fermi Paradox that the evidence currently supports. Not a single catastrophe, not a conspiracy of silence, not a physical impossibility, just the quiet, cumulative weight of entropy and transformation, and the narrowing of the window during which a civilization is both capable of leaving a mark on the cosmos and motivated to do so. The window may be very narrow indeed, narrow enough that across billions of years and billions of attempts, it opens and closes so quickly that no two civilizations have ever found themselves looking outward at the same moment from positions close enough to see each other's light. The darkness between stars is not empty. It is full of closed windows, and ours is open right now for however long it remains so. We began with a question asked over lunch. A man set down his fork in a cafeteria in the desert and asked where everybody was. The question sounded casual. It was not. It was the compression of an enormous mathematical contradiction into 7 words. A contradiction between what the numbers said should exist and what the evidence showed actually existed. Between a universe old enough and large enough and chemically rich enough to have produced intelligence many times over and a sky that returned. In every direction and across every frequency that human instruments could reach absolute silence. We have now followed that question as far as the current evidence allows. We have examined the scale of the galaxy and the age of its stars. We have traced the history of the search from Drake's 4 months of listening in 1960 to the decade-long operations of breakthrough listens scanning millions of stellar systems across frequencies that would have seemed fantastical to the pioneers of SETI. We have considered the easy explanations and watched each one fail under the weight of the assumptions it required. We have examined the great filter and its candidates from the improbable chemistry of the first self-replicating molecule to the improbable contingency of the ape that learned to write. And we have arrived at the possibility that frightens researchers most, that the filter may not be behind us at all, that it may be operating right now, that the silence we observe in the cosmos may be in part a preview of the silence we could become. The question is what to do with all of this. Not politically or practically, though those implications are real and urgent, but existentially. What does a species do when it has mapped the full contours of its own precariousness and found them more severe than it suspected? The first thing it must do is resist the temptation of false comfort. There are reassuring framings of the Fermi Paradox. The zoo hypothesis offers the warmth of being watched over, of existing within a larger community of minds that have chosen out of wisdom or kindness to give us space to develop on our own terms. The rare Earth hypothesis offers a different kind of comfort, the comfort of uniqueness of being so special that the silence around us is simply the silence of a universe that has not managed anywhere else to produce anything like us. The communication mismatch hypothesis suggests that we are simply not yet sophisticated enough to hear the conversation that is already taking place around us, that we are newcomers to a civilization-filled galaxy who have not yet learned the language. Each of these framings contains a genuine possibility. None of them can be ruled out with the evidence currently available. Any one of them might be correct. And yet clinging to them as certainties, treating them as conclusions rather than hypotheses, is a form of motivated reasoning that the evidence does not justify and that the stakes of being wrong do not permit. The silence is real. Its most rigorous explanation, the one that requires the fewest unsupported assumptions, is that something about the path from intelligence to enduring interstellar civilization is extraordinarily difficult. Not merely challenging, not merely costly. Extraordinarily difficult in the precise sense that almost nothing that begins the journey completes it. The Great Filter is real, in the sense that its existence is required by the observation of total silence in a galaxy old enough that the silence would otherwise be impossible. Where it sits remains uncertain. That it exists does not, and the existence of the Great Filter, wherever it sits, has implications that are difficult to absorb and impossible to ignore. If the filter is behind us, then we are almost certainly alone, not in the poetic sense of feeling isolated on a pale blue dot. In the literal sense, the only technological civilization in a galaxy of 400 billion stars, possibly the only technological civilization in the observable universe, a structure containing approximately 2 trillion galaxies, each comparable in scale to our own. Every piece of music ever composed exists nowhere else. Every mathematical proof ever derived, every act of compassion ever extended across the space between two minds, every moment of understanding that has ever occurred in the 300,000-year history of our species is cosmically unique. If we fail, there may be no one to try again. Not in this galaxy. Not in any galaxy within the reach of our light. The experiment of intelligence run once across the entire visible universe ends with us. That loneliness carries a weight that is difficult to fully absorb. We evolved in social groups. Our psychology is built for connection. The idea of radical cosmic isolation, of being genuinely and permanently alone in the way this scenario implies, runs against every instinct the species possesses. And yet the evidence, if abiogenesis or the eukaryotic transition or the emergence of intelligence, is the filter points in that direction. The silence is our solitude. The stars are beautiful and indifferent and empty. But if the filter is ahead of us, the implications are different, and in some ways harder to sit with, because they do not concern what we are. They concern what we must become and whether we are capable of becoming it in the time available. A filter ahead of us means that civilizations like ours arise regularly enough. That intelligence, once it appears reliably, reaches our current level of development, that the galaxy has produced across its long history many species capable of splitting atoms and sequencing genomes and asking Fermi's question, and that something systematically, reliably, and thoroughly prevents those species from surviving the transition to something more durable. Something that requires not merely intelligence, but wisdom, not merely capability, but restraint, not merely the power to reshape a planet, but the institutional and ethical architecture to manage that power across centuries and millennia without catastrophic failure. This means the 21st century is not merely an important century in human history, it is potentially the most important period in the history of life on this planet. More consequential than the Cambrian explosion, more consequential than the asteroid that ended the age of dinosaurs, more consequential than the emergence of our own species. Because this is the period in which the question of whether humanity belongs to the category of civilizations that pass through the bottleneck, or the category of civilizations that do not, will be determined. This is the crossing, and the crossing by the logic of the Great Filter is where almost everything fails. The astrophysicist Carl Sagan wrote in 1980 that he had a foreboding of an America in his children's time when, clutching our crystals and nervously consulting our horoscopes, our critical faculties in decline, unable to distinguish between what feels good and what is true, we slide almost without noticing back into superstition and darkness. He was writing about the importance of science and rational thought, but the warning extends further. The capacity that allows a civilization to navigate the bottleneck is not merely technological. It is not merely a matter of developing cleaner energy, or safer AI, or better biosecurity protocols, though all of those matter enormously. It is a capacity for long-term thinking, for caring genuinely and structurally and institutionally about people who have not yet been born, about consequences that will unfold over centuries, about the species as a continuous project rather than a series of disconnected present moments. This is the capacity that our evolutionary heritage conspired against. Natural selection did not reward thinking about consequences 10,000 years hence. It rewarded thinking about consequences that would affect reproductive success within a lifetime. Our brains are exquisitely sensitive to immediate threats and immediate rewards. They are poorly calibrated for the kind of long-horizon reasoning that existential risk requires. The mismatch between the cognitive tools evolution gave us and the cognitive tools that surviving the bottleneck demands is itself a form of filter, a filter built into the architecture of intelligence. Whether it is an insurmountable filter is the question on which everything depends. There are reasons for something other than despair, not naive optimism, not the comfortable assumption that things will work out because they always have worked out, that confidence is itself a failure to reckon honestly with the historical record, but something more grounded, more earned, the recognition that the same species that created nuclear weapons also created the Nuclear Non-Proliferation Treaty. The same species that began unraveling the planet's climate systems is the species whose scientists first detected the unraveling and raised the alarm loudly enough that some fraction of the world's governments began to respond. The same species that is developing artificial intelligence systems of potentially transformative power is also the species actively working on the alignment problem, building institutions dedicated to ensuring that the technology develops in ways compatible with human flourishing. These are not solutions, they are not guarantees. The distance between a treaty and a resolved risk, between a warning raised and a danger averted, between a problem identified and a problem solved, is vast and is crossed by political will, institutional competence, sustained attention, to luck in proportions that history does not allow us to predict with confidence. But they are evidence that the capacity exists. That intelligence is not purely a mechanism for generating and deploying destructive power. That somewhere within the cognitive architecture that also produce nationalism and tribalism and short-termism, there is the capacity for the kind of enlarged perspective that survival across deep time requires. The astronomer Carl Sagan again put it in terms that have not been improved upon in the decades since. We are a way for the cosmos to know itself. We are made of star stuff. The carbon in our bodies, the oxygen in our lungs, the iron in our blood, all of it was forged in the nuclear furnaces of stars that lived and died before our sun was born. We are the universe turned back on itself, examining its own history, asking its own questions, capable of understanding the processes that created us. That capacity for self-knowledge is not merely a human achievement, it is a cosmic one. It is, as far as we can determine, unique in the observable universe. And its continuation or its loss is the stakes of the question Fermi asked over lunch in 1950. We do not know where the great filter sits. This is the most honest thing that can be said after everything we have examined. The silence of the cosmos is consistent with a filter that lies in the distant past among the nearly impossible chemistry of the first living cell, and it is equally consistent with a filter that lies just ahead of us in the technological adolescence that we are currently living through. The evidence does not yet discriminate between these possibilities with the precision that would allow a definitive answer. We would need to find life elsewhere to begin collapsing the uncertainty. We would need to find complex life to collapse it further. We would need to survive ourselves for long enough and on a large enough scale to know whether the filter that stopped almost everything else has stopped us too. In the meantime, we exist in the uncertainty. We are a species in the middle of the crossing, unable to see either shore, clearly navigating by instruments. We are still learning to read in conditions that have no precedent in our evolutionary history. The universe offers no guidance. It does not distinguish between civilizations that make it through and civilizations that do not. It does not weight the odds in favor of the curious or the careful. or the wise. It is, as it has always been, indifferent. The laws of physics apply equally to civilizations that endure for millions of years, and to civilizations that burn out in a few centuries. The stars do not care which category we occupy. But we care. This is the thing that the Fermi Paradox followed to its end ultimately reveals. Not a fact about the universe, but a fact about us. We are the only known entity in the cosmos that is capable of caring about the cosmos, of finding it beautiful and strange and worthy of understanding, of looking out at 400 billion stars and feeling something other than indifference in return. That capacity for caring, for wonder, for the kind of sustained attention that turns a question asked over lunch into 75 years of scientific inquiry, and still counting, is not nothing. It is from the perspective of everything we can observe everything. The question Fermi asked is still open. The silence is still real. The filter is still somewhere in the chain between dead rock and lasting civilization, and we do not know which side of it we stand on. We are still broadcasting, still listening, still reaching into the dark, with instruments that grow more sensitive with each passing decade, still waiting for the answer that would change everything, still not finding it, but we are still here, still asking, still in the vast and patient darkness of a universe that has been running its silent experiment for 13 billion years, keeping the lights on. The window is open. For now,